Thanks for joining. My name is Daniele, and today I'll present to you Pure, payments with ultra-wideband relay protection. This is work developed at ETH Zurich with the colleagues that you see on the slides. Let me start by introducing you to the problem that we're trying to tackle. In a contactless payment, the cardholder expresses its willingness to pay by placing their card or their phone next to the terminal. And of course, when the two devices are far away from each other, no transaction should take place. This is undermined by a relay attack in which an adversary creates a channel between the two devices, thereby making them believe that they're close and that they should execute a transaction. This can be a lucrative attack. For every relay, an attacker can execute on behalf of the victim a transaction of up to $50 without even requesting a PIN, or up to a card limit with an unlocked phone with some devices. So this is, of course, a problem. And in terms of relay attacks, we divide between logical layer relays that introduce a significant amount of delay. For example, two phones connected to the internet. And more powerful ones, these are at the physical layer, introduce lower delays. For example, a cable or specifically built hardware, as you see in the picture here. And of course, you might think nobody would place their phone on top of this hardware or their card, but attackers can be smart. They can package their relay into something that looks like a terminal and trick the victim into placing their card on top of this to execute a low-value transaction, while actually everything is relayed to another real terminal where the transaction takes place. Existing countermeasures mainly tackle logical layer relays, while they fail to prevent physical layer relays. And with Pure, we're trying to prevent any kind of relays, ensuring that if a transaction takes place, it means that the card and the terminal were close together. Pure extends the Mastercard kernel. This is one of the protocols that can run a contactless transaction. And what's relevant is that every card has a public secret key pair that is authenticated through a PKI. And at the really high level, after a series of exchanges, the card commits to a transaction by computing a MAC over some transaction parameters with the symmetric key shared with the bank, as well as a signature over these transaction parameters. The terminal can verify the signature and forward the application cryptogram to the bank that then either confirms or declines the transaction. We extended this protocol with an ultra-wideband distance measurement that ensures that the two devices are close together. And because of this, we need ultra-wideband chips, which means that Pure specifically targets mobile phones and not on-device cards. For the remaining of the talk, I will use card and phone interchangeably. In terms of threat model, we assume the phone and the terminal to be trusted. And here, with terminal, I mean the terminal that is connected to the backend. And this is because the terminal executing the transaction in the backend, if this one is misbehaving, it can be easily detected through fraud detection. However, an adversary sitting in the middle, which we assume to be a Dolevia adversary that creates a relay, can execute a transaction on behalf of the victim while actually leaving no trace of himself within the payment ecosystem. Delving a bit deeper into the protocol, on the left side, you see the Mastercard kernel as a block diagram, and I will explain each block as we build the extension. So as I said, the main block that we introduce is a ranging sequence. It takes as input a ranging key. This is a shared secret between the two devices, the card and the terminal, and outputs an upper bound on the distance. Now, at the beginning of the protocol, the Mastercard kernel is selected, and subsequently, with the get processing option, the card communicates to the reader its capabilities. And there we use a reserve for future use bits to communicate that the card is able to execute ultra-wideband. This is to be backward compatible with, for example, physical cards. If the card can execute ultra-wideband, we execute a Diffie-Hellman exchange that creates a shared secret which is not yet authenticated. However, we can already use this to execute ranging and compute a bound on the distance. Meanwhile, in parallel over NFC, the transaction can continue, and the terminal starts reading field from the card, for example, the certificate authenticating the public key. And in the end, we have the authentication step that we saw before, which we modified to authenticate the key exchange above. We model this extension using Tamarin. This is a formal protocol verification tool, and we proved secrecy of the ranging key and injective agreement on ranging key and the transaction. This is important because it ties together the ranging and the transaction, and moreover, it shows that there cannot be downgrade attacks because it means that the get processing option is authenticated. Now that you've seen at a high level the protocol, we're going to zoom in into the ranging block to show you which were the challenges that we had to tackle. We used ultra-wideband ranging. This is the state-of-the-art for secure ranging, and it's widely supported in phones. At the protocol level, it's rather simple. The two devices derive nonces from the shared secret, which they use to do a time nonce exchange. Measuring the round-trip time, they're in the end able to measure the distance between each other. To understand the problem of ultra-wideband, we have to actually look at how these nonces are encoded at the physical layer. And these nonces are just a sequence of bits, and each bit is encoded into pulses, either plus or minus 1. And these pulses have low power because of regulatory reasons, which means that when we send them through the channel, because of multi-channel and noise, the receiver cannot distinguish these pulses reliably. So what receivers do is they generate the signal that they're expecting, here the template, and they shift it in time, looking for correlation within the received signal. For example, here, when it aligns with the direct path, we see a peak, which is the early peak and corresponds to the true distance. And again, here we have another path, the main peak, and so on. And as you can see, the main peak does not have to be the early peak. For example, if there's attenuation on the direct path. This makes it harder for the receiver to verify and find the time of arrival. And indeed, the main issue with ultra-wideband is that it is hard to distinguish a good channel on which only a fraction of pulses are correct from a bad channel where all the pulses are correct. This is the principle that made ghost peak attack possible. It's an attack presented in USENIX 2022. And the idea is that the adversary simply sends at a high power random pulses, and it hopes that they correlate well with the incoming signal. If that ghost peak is selected, the distance is reduced, and in the case of pure, a transaction takes place, which we don't want. In general, solving this problem is quite hard, but we managed to solve it in the specific case of contactless payments where the channels are more favorable. And we did this by using an absolute threshold and selecting the first peak that is above this threshold. To give you an intuition why this is actually secure, here you see how the peak height changes as the number of correct pulses changes. And of course, the more pulses are correct, the higher the peak. Now, we see that going from the green line to the orange line, so increasing the power, the adversary gets an advantage. It gets higher peaks. However, increasing the power even more doesn't change anything. And the reason is that no matter how strong these pulses of the adversary are, the receiver has an operating range and will clip these pulses. And if you think that its operating range will be normalized between 0 and 1, no matter the attacker power, every pulse will only contribute with a certain amount to the overall peak, which means that an absolute threshold forces the adversary to guess a certain amount of bits. And with this, we can drive down the probability of a ghost peak attack to 2 to the minus 48, which is what is required for contactless payments. Putting it all together, we made a proof of concept implementation with 2 Android phones. And here you see that we had to equip them with an external UWB chip. This is because the API to access the UWB chip are still in development, and we needed better access to the ultra-wideband chip. With our experiment, we see that our threshold is reliable in contactless payments channels. We have a 2% false rejection rate when preventing relays above 46 centimeter. And in terms of the overhead introduced, because we can reuse the certificate exchange and the authentication step, the main source of overhead is the Diffie-Hellman exchange, which takes roughly 41 milliseconds, and it's 5 to 9% overhead on top of a normal transaction. As any system, Pure has some limitations. The main one is deployability. It can only target phones, and so it cannot protect physical cards. And the second issue is that in order to provide security to the overall ecosystem, it needs to be largely deployed on terminals. Having said this, if Pure were to be deployed, it would effectively prevent any kind of relay attacks above 50 centimeter. The extension was proven secure using Tamarin, and we analyzed down to the physical layer the distance reduction attacks, showing that Pure is not vulnerable to ghost peek, and while maintaining reliability. And with this, I would conclude my presentation, and I'm open for questions. Thanks.